Hi there. Now in this video what I want to do is show you how we can use this version of the Taylor expansion or Taylor series to express xc to the power minus x in powers of x plus 1 up to and including the term in x plus 1 all squared. So to do this, what we need to do is just say that let f of x, just define f of x as being the function xe to the minus x. Now, if we're going to expand this in terms of x plus 1, then comparing x plus 1 with x minus a would have to be negative 1. So we're going to put here where a equals negative 1. And if we do that, okay, then by Taylor's expansion, we're going to have, I'll just put here, so f of x will be equal to f of minus 1 for the first term, and then for the second term, it'll be the first differential of f of x, where x is equal to minus 1, and then this is multiplied by x plus 1. Okay, x minus minus 1, giving us the x plus 1. And for the next term, that will be the second differential of f of x, where x is equal to minus 1. And we divide this by factorial 2 and multiply it by x minus a, x minus minus 1. So that'll be x plus 1, and that is all squared. There'll be other terms, okay, even though we are going up to the term in x plus 1 all squared. So what we need to do is start to work out some of these values in these terms. So if we just have f of x, then we'll put it back in as f of x equals xe to the minus x. So for this first term, f of minus 1, it follows from here, let's just put it follows, okay, it follows that f of minus 1 is going to equal minus 1 here multiplied by e to the power minus minus 1. So that's just minus e. Now next term, we need to find the first differential of f of x. So if we're trying to find the first differential of f of x, we've got to use the product rule. So if we take x and multiply it by the differential of e to the minus x, that's going to be minus e to the minus x. And to this we add, and we'll take e to the minus x, and we multiply that with the differential of x, which is 1. And if we tidy this up, what we've got is minus x e to the minus x, and here plus e to the minus x. So it follows from this that f dash of minus 1, well, that's going to be plus 1 here, e to the minus minus 1, so that's just going to be e. And then we've got plus e to the minus minus 1, so that's plus another e. So in other words, we've got 2e. Now for this last term here, we need to get the second differential of f of x. So in other words, for f double dash of x, we need to differentiate this term here. Well, the differential of xe to the minus x, we just did it. It was here. Only if we've got a minus here, we've just got to negate both these values here. So we're going to get xe to the minus x minus e to the minus x if we use the product rule on that first term. And then the differential of e to the minus x, well, that's going to be minus e to the minus x. And if we simplify this, we end up with x e to the minus x minus 2e to the minus x. So from this, it follows that if we work out f double dash of minus 1. Then for the first term here, we're just going to get minus e. And then for this term, we end up with minus 2e. So a total then of minus 3e. So we can now find the Taylor's expansion then of f of x, that is xe to the minus x, by substituting our values now into the Taylor expansion here. So therefore, what we've got is xe to the minus x is going to be equal to f of minus 1, which is minus e. And then to this, we plus f dash of minus 1 times x plus 1. So that's going to be plus 2e multiplied by x plus 1. And for the last term, we've got f double dash of minus 1 over 2 factorial times x plus 1 all squared. So f double dash of minus 1 is minus 3e. That's divided then by 2 factorial multiplied now by x plus 1 all squared, and so on. And if we just tidy that last term up once more, we end up with minus e plus 2e multiplied by x plus 1, and then minus 3e. 2 factorial is 2, so we'll just put that over 2, and that's multiplied by x plus 1 all squared, and then plus, and so on. Now, it'd be interesting at this stage just to compare the graphs of xe to the minus x with our Taylor's expansion of xe to the minus x. And I've done that for you here. You can see in red I've got the graph then of y equals xe to the minus x, and in blue we've got the Taylor's expansion for that. Okay, and notice how close the graphs are to one another in the vicinity of x equals minus 1. So Taylor's expansion is going to work for values of x very close to x equals minus 1. If you go beyond that, you're going to find, like when x is 1, you're going to have a huge difference between your two values. So this is where Taylor's series comes into its own for approximating values close to the vicinity of your value for a. Okay, well, I hope that's given you an idea anyway how we can go about expressing a function of x in terms of ascending powers of x minus a by using Taylor's series then.